Hey guys, so let's start our circular motion, our study of circular motion. For this level, we're just going to be concerned about uniform circular motion. Uniform, I'll talk about that in a second. So with this piece, what we're going to do is talk about the velocity and acceleration of an object moving in a circle, and then we'll get some definitions on here: period, frequency, and speed. So it's just kind of laying the groundwork for some analysis. We're not going to be dealing with forces yet, but we are going to talk about some things that will lead to it. So it's mostly vocabulary, including the mathematical definitions of these things. So first is uniform circular motion. So uniform circular motion means that we have constant speed. So the uniform part of this means constant speed. So if I have an object moving in a circular path like this, so here's an object, it's moving in a circular path. Let me go ahead and animate it. So we can see that it's just following a nice clean arc, not a parabola. This is not projectile motion. And so this vector coming off of it, this is your velocity vector. So we can see that the velocity, although it's going to keep the same magnitude, the same speed, it's constantly changing direction. So we have constant speed, but constant change of direction. So constant change of direction. Yeah. So the constant change of directions means that I have a change in velocity. And if I have a change in velocity, this means that there has to be some acceleration. So for circular motion, we have an acceleration. I can show it here. So this is that new vector. And if you look at it, what you'll notice is that this vector always points towards the center of the circle. This is different from projectile. Projectile, it always points towards the ground. In circular motion, it always points towards the center. And so we can, let's go ahead and let me take a step back. So that velocity that we're talking about, the velocity, that's called tangential velocity. Tangential velocity. And that's because the velocity is tangent to the circle. But now the acceleration, so the acceleration is always pointed towards the center. So our acceleration has a special name. It's called centripetal acceleration. Centripetal. And what that means is center seeking, centripetal acceleration. So this is center seeking. It's always pointed towards the middle. Always pointed towards the middle. It's always pointed towards the middle. Center seeking. And we just put a little C on it. That means that it's centripetal acceleration. So here's my diagram up here. You can see I have some tangential velocity. If you want, you can put a little T on that just to show that it's tangential. We have another type of velocity that we'll talk about in the next level, and that has to do with just it's called the angular velocity, but we're not going to worry about that now. It's just how fast is it moving around in a circle, and then centripetal acceleration always points towards the center, wherever it is. All right, so I think we're done with that, but so let's get a definition. So centripetal acceleration. Centripetal acceleration. So AC is going to be the v squared, the velocity of the particle divided by the radius. So that is radius of the circle. So centripetal acceleration of the object will just be how fast is it moving divided by how far is it from the center. And that's our centripetal acceleration. So two things to note here. We got a different color. When we look at acceleration versus radius and acceleration versus velocity. So let's look at acceleration versus velocity. So as the velocity increases, the acceleration also increases, but it's the square. So we end up with a quadratic. So my relationship of centripetal acceleration to the velocity is a square. So how's it related to the radius? So centripetal acceleration to the radius. If we hold the v squared constant, then I see it's 1 over r. So we end up getting an inverse function. So that's my relationship between centripetal acceleration and radius and with velocity. So what kind of situations does this come up in? All kinds of stuff. Going around a corner in a car, amusement park rides, twirling something on a string, all kinds of things. But what we're going to do now is we're going to get into these other terms, period, frequency, and speed. So let me change back to green. Okay, so let's start with period. The period is it refers to the time it's going to take the object to go all the way around. So one complete cycle. Let me speed this up a little bit. So like from there, the time it will take at constant speed to go all the way back around to wherever it started. And for period, we use big T. And the period is defined as 1 over the frequency. And so we can redefine this. So the period is the time. That's the time it takes. The time it takes to go all the way around. So we can think about that. We can think, okay, well, how long is it going to take this thing to go all the way around? And it takes 1, 2, 3, 4, 5, 6, 7.5. Okay, so about 7.5 seconds, whatever. That would be my period. But now here's the question: what's frequency? So frequency, we use little f. And we can just rearrange this. So frequency is the inverse of the period. And this is how many. So how many times does it go around in a certain amount of time? So if I wanted the frequency, I could say, well, it's going to do 1 revolution every 7.5 seconds. So we could say like 1 revolution, or we could say it's revolutions per time. And the units on this thing are inverse seconds. Those are the units. So it's how many revolutions per time. So this would be like RPMs or revolutions per second. That's what we're talking about frequency. Period, we're always talking about time. How long does it take to do 1 complete revolution? And what you're going to have to be able to do is just go between these. But we'll do lots of practice. You'll start to get the hang of it. So how can we tie this all into acceleration and velocity with period and frequency? It's not too hard. If we think of velocity is, how far does it go, the change in position over time. And then in a circle, the change in position, what we want to do is go all the way around one time. If I go all the way around one time, then I've gone 2 pi r, which is my circumference. And the time it takes to go all the way around is my period. So we get this new equation. The velocity can be determined if I just know the radius and the time. I can use this to figure out the velocity. But now we also know that period is 1 over frequency. So we know that I can substitute here. So this would also be equal to 2 pi r times f. So these are equivalent. Frequency is 1 over t. You see the substitution there, t to f. Yeah? Okay, and then I can even take it and put it, we could say, well, the acceleration, the centripetal acceleration is v squared over r. And then I can substitute here. So I would get 2 pi rf, that's my velocity up here, squared over r. And if we simplify that, I'll get 2 pi f squared times r. That'll be an r squared, and then I'll cancel it, so we get that. And I could substitute and get another equation, so I get 2 pi divided by the period squared times r. So these are all equivalent. Anyway, you have a couple equations. You'll just mess around. You got to substitute and move between them. And you'll be doing that in the practice. All right.